Okay, the next topic is mechanics of breathing made easy. And I put easy in quotes because I don't know if it's exactly easy. This is actually where I did my PhD in mechanics of breathing, so I guess that probably means I should be able to teach it better than the other sections. I don't know if that's true. Okay, the next topic is mechanics of breathing, and I said made easy. I'll make it as easy as I can. This is actually where I did my PhD in mechanics of breathing. I guess that means I should be able to teach it, but I'm not sure if that's the case. All right, so we'll start with a fairly simple diagram of the respiratory system. So there's the lungs, chest wall, muscles of breathing. The space that the lungs fit in is called the pleural space. It's not really a space there. It's kind of more of a certain theoretical space. The lungs sit in a compartment that is the chest wall. We call that the pleural space. So rather than talk about the whole system, I'm going to make a model of it. So start with the chest wall, the airway. We'll replace all those alveoli with a single alveoli, and we'll replace all the muscles of breathing with a single muscle of breathing. So we have the airway, alveoli, the chest wall, the muscle, and this here is called the pleural space. And the whole system breathes. So I can make the model breathe just the same way as the lung breathes. All right. What we need to look at when we're talking about the mechanics of breathing is what the sources of impedance are. And in the respiratory system, there's really two main sources of impedance. This impedance is everywhere, but the main ones are the airway and the alveoli, or the lung tissue. So what are impedances? There's actually three impedances in all physical systems. And we can illustrate them here by looking at Sir Isaac Newton pushing on this model, which has an apple and a spring, and the apple is sitting on the surface of a desk. So there's three different things that are opposing the movement of that apple when he pushes on it. The first one is elastance. That's where he's distorting an elastic structure. An elastic structure is something that wants to spring back to its resting position. So in this system, it's obviously this spring. When he pushes, he compresses the spring, and it wants to decompress or spring back. The second one is resistance. The apple needs to slide along this surface, and there's friction on the surface between the desktop and the apple, and that offers resistance, and he needs to overcome resistance as he pushes along. The third one, which is not as obvious, is inertia. So even if the apple was floating in space and it wasn't moving, he would need to still exert a force on it to get it moving, to get the mass away from its resting state, which was zero velocity. So each of these impedances is in proportion to something. Elastance is in proportion to displacement. He needs to push harder and harder as he compresses that spring more and more. Resistance is in proportion to velocity. The faster he pushes, the more resistance there is between the apple and the surface of the desk. And inertia is in proportion to acceleration. The faster he accelerates that apple, the more force he needs to exert. So those are the three impedances in any physical system. In your breathing system, luckily, this one is not very important. The mass of the air, the mass of the chest wall, the mass of all the lung tissue is rather trivial. So when you breathe, you're not doing very much work at all to overcome the inertia of the respiratory system. If you panted like your dog, then inertia becomes much more important. But in you guys at rest, in most patients that you look at, elastance and resistance are the dominant sources of impedance to breathing. So here's the airway offering one impedance. The lung tissue, the alveoli, offers another impedance. So to get air to move through a tube like an airway, you need the pressure at one end to be greater than the pressure at the other end. Whenever you have a difference in pressures along a tube, air will move through that tube. And here's a graph showing how as you increase the pressure difference between here and here, the flow changes. And for the most part, while we breathe, that's quite linear. As you increase the pressure gradient across an airway, the flow increases. You can actually change that relationship. When you get to very high flows, this relationship becomes much flatter. You need much greater increase in pressure to get an increase in flow, and that's because you've got turbulence in the airway. When you guys are breathing, there's not much turbulence, but there are conditions where you want to have turbulence, like when you cough. So when you cough, what you do is you increase the pressure gradient so much, you get areas of flow where you've got turbulence, which is really good for ripping particles off the side of your airway. All right, so the slope of that relationship, or the inverse of that slope, is what's called resistance. So the resistance of the airway relates to how much flow you can get when you create a pressure gradient along your airways. And resistance increases as the airway gets longer, and it increases as you make the radius get bigger. Sorry, the radius gets smaller. When I make that radius of the airway decrease by half, so I made the airway half as wide as it normally is, the resistance increases 16 times, r to the fourth. So resistance is the property of the airways that's resisting flow. And in diseases where the airways get narrow, like asthma and COPD, then there's a whole lot more resistance to getting airflow through the airways. Okay, if we go down and look at the alveoli, alveoli can get bigger when you apply a pressure, when the pressure inside the alveoli gets bigger. So I made the pressure get bigger, the alveoli got bigger. And if we look at the relationship of that, as pressure increases, volume increases, and again, that's for the most part linear. And the slope of that is compliance, and the inverse of that slope is called elastance. So usually, when we're talking about the stiffness of the lungs, we talk about compliance, because that's a word that makes sense to the patients, it makes sense to physicians. If you have a compliant lung, it means it's nice and stretchy. As the lung gets stiffer, the compliance goes down. And compliance is determined by the elastic properties of the tissue. So at this point, hopefully you're comfortable with the idea that there are two main sources of impedance in the respiratory system. Resistance, mainly due to the size of the airways, and compliance, due to how stiff the lung tissue is. All right, so now we'll look at how we breathe. So a balloon, which I already said, can be inflated by applying a positive pressure at the opening. So if I applied a pressure of plus 5 centimeters of water, so that's enough pressure to lift a column of water up 5 centimeters, then that balloon would inflate. The other way I could make the balloon inflate is to apply a negative pressure around the balloon. So I could put it in a box and make the pressure in the balloon negative 5 centimeters of water. And you're going to read a lot about positive and negative pressures when you're reading about mechanics in the different patient problems that you look at. Negative pressures don't really exist. There's no such thing as a negative pressure. When they talk about negative pressure, they mean that the pressure in this box is 5 centimeters of water less than the pressure in the atmosphere. So you can imagine this is actually a very simple model of the respiratory system. Here's the chest wall, here's the lung inside it. If the pressure in this pleural space is 5 centimeters of water less than in the atmospheric pressure, then that allows the atmospheric pressure to inflate the lung. And that's exactly the way you guys are right now. The pleural pressure in you is 5 centimeters of water less than in the atmosphere, so your lungs are inflated because of the lower pressure around the lungs than the pressure in the lungs. So let's look at how we breathe. So right now, when you're sitting there at rest, if there's no muscles active, so let's imagine you've just breathed out, you haven't breathed in yet, there's no muscles active, there's no breathing taking place, and your pleural pressure is 5 centimeters of water less than the atmospheric pressure. And that negative pressure, or subatmospheric pressure in your pleural space is what's keeping your lungs open. That's defined as functional residual capacity. It's the resting position of the respiratory system. How do you breathe in from that starting point? So you've just breathed out, you're nice and relaxed. First thing you do is you turn on your diaphragm and your external intercostals, and that essentially pulls on the pleural space, and it makes the pleural pressure become more negative. So you activate your inspiratory muscles, pulls on the pleural space, and makes the pleural pressure more negative, maybe down to minus 10 centimeters of water. What that does is pulls on the alveoli to make it bigger too. So let's look at a breath. And what we're going to do is start off by making it as simple as we can by getting rid of the airway. We're just going to look at what the alveoli are doing. So there, the airway's gone. There's no more resistance in this lung. The only thing we have to overcome is the elastic properties of the lung itself. So first of all, we'll get the person to breathe. So he took a breath in, and then he breathed out. Inspiration, expiration. We already talked about how the pleural pressure was minus 5 centimeters of water at the beginning of that breath, and that negative pressure in the pleural space was what was keeping the lung open. So you can imagine that as I took that breath in, the pleural pressure had to become more negative to make the lung bigger. So we'll look at what the pleural pressure did over the course of the breath. And there it goes. So the inspiratory muscles are contracting, making pleural pressure more negative, and the lung volume increased in direct proportion to how much negative the pleural pressure became. It's a very simple system. The harder you pull, the bigger the lung volume gets. So that shows the pressure that I need over the course of a breath to overcome the elastic properties of the lung without having to overcome any resistance. Now we're going to put the airway back in, and that adds resistance. So there's the airway back in. Now we're going to look at flow down, up and down the airway at the same time as we've got the volume change in the lung. So we'll get the person to breathe. So you can see they breathed in, they breathed out. During the inspiration, there was inspiratory flow. Let's go down in that direction. And during the expiration, there was expiratory flow, air moving back out in this direction. So now it's a bit more complicated. The pleural pressure, as well as overcoming the elastic properties of the lung, with the volume change, needs to overcome the resistive properties of the airway to give rise to this flow. So we'll see what the pressure does. So there's the inspiration and the expiration, inspiratory flow, expiratory flow. Now down here, it looks a bit complicated, but it's not too complicated. There's three things there. The red curve is the same red curve that we had before. That's the pressure that you needed to overcome the elastic properties of the alveoli, giving rise to that volume change. But at the same time, you needed to overcome the resistive properties of the airway, which give rise to this flow. So during the inspiration, the red curve is how much you needed to overcome the elastic properties. The black curve is what the pleural pressure actually did. It was more negative during inspiration when you had the airways there than it was without the airways. And the difference in those two curves, the blue, is the pressure that you needed to overcome the resistance of the airway. So you can see during the expiration, the pleural pressure is actually not as negative as it was when we didn't have the airways there. The reason for that will become evident in a couple of slides. All right, so what we're going to do now is we're going to look at three things. We're going to look at the lung recall pressure, the pleural pressure, and the pressure in the alveoli during the breathing cycle. So we start at FRC. So that's the volume you're at the beginning of a normal inspiration, right here. So at that point, we've already said that that the pleural pressure is negative, and it's overcoming the pressure needed to oppose the recoil pressure of the lung. So at that volume, the recoil pressure of the lung is about 5 centimeters of water. What that means is you either need a positive pressure inside it, keeping the balloon open, or you need a negative pressure outside it, keeping the balloon open. And in the case of the respiratory system, at that resting volume, the pleural pressure is -5, keeping the lung open. So because the lung recoil pressure is completely opposed by the pleural pressure, the alveolar pressure is 0. It's a nice static system. Pleural pressure is keeping the lung open. There's no pressure in the alveoli. Now we're going to move up to what happens during the inspiration, sort of halfway up. At this point, the lung volume is bigger. It's more stretched. So the recoil pressure is bigger. It's a stretched tissue. So we'll say the recoil pressure of the lung is 7 centimeters of water. What that means is you need to have a pressure outside it here of -7 to oppose that pressure and keep it at that volume. But the pressure when we're taking a breath in is actually more negative. It's -8. So the muscles are working hard enough that the pressure around the lung in the pleural space is more negative than the pressure you need to overcome the elastic properties of the lung. So because of that imbalance, you're pulling harder on it than you need to keep it at that volume. The pressure inside the alveoli becomes negative because you're pulling on the whole system. So now you've got a negative pressure in the alveoli. That gives you a pressure gradient along the airways. So that negative alveolar pressure is what's overcoming the resistance of the airways. Then, when you get up to the end of your inspiration, to the highest volume you're going to get to, again, the lung is more stretched up there, so the recoil pressure is even bigger, maybe 10 centimeters of water. You need 10 centimeters of water to keep the lung at that volume. And that's exactly what you're providing with the muscles of breathing. You're making the pleural pressure -10, completely overcoming the elastic properties of the lung. Because there's no imbalance there, the pressure in the alveoli is 0, so there's no gradient along the airway, and there's 0 flow. Now if we look on the way out, during the expiration, we're going to stop at the same volume that we stopped on the way in. And we'll look, so the recoil pressure of the lung there is exactly the same. You need 7 centimeters of water pressure to keep the lung at that volume. And if you look at what the pleural pressure is at that point, it's only -6. So that means the muscles of breathing, or the recoil of the chest wall, is only providing -6 centimeters of water in the pleural pressure. That is not enough to overcome the recoil properties of the lung. So that allows the lung to compress the alveolar contents, and the alveolar pressure is now 1 centimeter of water. So because you're not working hard enough to keep the lung open, the lung deflates, compressing the contents in the alveoli, giving you positive pressure, which produces airflow in an expiratory direction, overcoming the resistance of the airway. So summary there is that with no muscle activity, pleural pressure is negative, opposing the elastic recoil of the lung and the chest wall. That's functional residual capacity. During inspiration, inspiratory muscles make pleural pressure more negative, overcoming elastance and resistance. And during expiration, the inspiratory muscles relax, allowing the lungs to recoil back to the resting volume of the respiratory system. So that's probably quite a bit more complicated than you will need to look at mechanics of breathing when you're looking at patients. It won't get into sort of individual resistances or elastances or what the sources are. But understanding how you breathe and what the forces are that you're coming, I think is helpful. So if, for example, you're looking at a patient with a restrictive lung disease, it's stiffer. It's going to take a lot more pressure for them to breathe in and out. So the pleural pressure will probably go from -5 to -20 or -30. They have to create a lot more pressure to overcome the elastic properties of the lung. Likewise, if you look at a patient with narrow airways, they're going to need to have a lot of pressure to overcome the resistance. So again, they'll need to generate more pressures overcoming the resistance. And those are kind of similar in that the patients are having to work hard to breathe in, but they're overcoming completely different impedances. And what we'll do in the large group session is look at some of the tests, mainly with spirometry, that are done to distinguish between restrictive diseases, where you've got stiff tissue, and obstructive diseases, where you've got narrow airways. I'll just show one more slide in the mechanics of breathing section, where it's a kind of an overview of the different diseases or mechanical problems that you can have. So you can have disorders of pressure generation. That's where you don't have enough strength to overcome the impedances of the respiratory system. You've got disorders of resistance. That's where the airways are narrow. Or you can have disorders of compliance. That's where the lung tissue is either stiff or floppy. So you can have abnormal anatomy, things like kyphoscoliosis, where the arrangement of the muscles is not optimal and you can't generate the same pressures you could with normal anatomy. You can have muscle weakness. You can have muscular dystrophy, stroke, chronic disease, and all of those diseases, and there's many other diseases obviously. You can have weak muscles, so you don't have the strength needed to overcome the impedances of the respiratory system. You can have disorders of resistance, like the obstructive lung diseases, where airways are narrow. So that would be asthma and COPD. You can have disorders of compliance. You can have diseases where the lung's stiff because it's not compliant enough, like the fibrotic lung diseases, which you will read about. And you can have diseases where the lungs are too floppy, so emphysema, which is actually something you get with chronic obstructive lung disease. So these are the obstructive diseases where the airways are narrow. And the restrictive lung diseases are the muscles, the diseases where you have weak or suboptimal muscle anatomy, and the fibrotic diseases where the lungs become stiff.